We're now going to look at a significant improvement to Euler's method. It's called, in your textbook, it's called improved Euler's method. It has many other names, but we'll just call it improved Euler's method. So this should look familiar. That's Euler's method. That's how, given a yi and the differential equation and a step size, we can estimate yi plus 1. This is part of Euler's method, but we're going to call this y star. And we're going to use it in this equation. yi plus 1 is yi plus h. But now I'm going to make a fraction. On top, I'm going to do f of xi, yi, plus f of xi plus 1, comma, y star I plus 1 over 2. This is the new improved Euler's method. So essentially what you do is compute yi plus 1 just like you did before. Only all we're going to do with that is name it give it a new variable name, yi plus 1 star. The actual value we're going to use for yi plus 1 is yi plus h. And look what we're doing here. Instead of just having f of xi, yi, we're adding up two values of the function at two different points and averaging it. That's all we're doing. So instead, let me go ahead and draw that line. What did we do? What are we doing? Before, with Euler's method, we just said x1, y1 is this point right here, and we're done. What this is doing is looking ahead right here and getting the slope at this point. It's taking that slope and this slope, adding them together and dividing by 2, averaging them. So it's very likely it's going to produce something more like that, getting us much closer. And then in the next step, we're going to do the same thing. Rather than just taking the slope of this and drawing a straight line, let's jump out to x2 and figure out what our estimate using regular Euler's method would be. Say it's here. Grab this slope by plugging it into f of xy. Average those two slopes, and maybe we end up here. I didn't mention this in the first video, but this being the formula for just Euler's method, this is a first order formula. It's like taking the first two terms of a Taylor series. It looks very much like a Taylor series. Going out one more term, where we would have an h squared over 2, and we would have to take the derivative of f of xy, is very expensive in a computer. And this, which does not have any new derivative in it, is very, very close to a second order estimate, which is excellent compared to a first order estimate. So we're getting a lot of improvement from the old Euler's method into the improved Euler's method. Let's take a look at an example that's going to look familiar, because this is exactly the same differential equation, initial value problem we did in the previous video. This is our little reminder, it's our cheat sheet of the improved Euler's method. So we're going to do the same thing. Let's estimate y of 3 at time 3 and use two time steps. So h again is going to be 1.5 for this problem. All right, I've already worked some of it out. We know y0, x0, y0. it was given to us right here. So then, this should look familiar. Y1 last time, didn't we get a 6.5? Well, we're just calling this a temporary variable right now. We're going to use it in the real computation of y1, not y1 star, but y1. And I wrote it down here again, y0 plus h times the average of these two function values. So now I plugged in the values. I plugged it into the calculator and I got y1 is 4.302. So this is our estimate of y1 or x1, y1. All right, now we're going to go up to the case where this was I equals 0. Now we'll go I equals 1, and we're just basically going to be doing the same thing. We know x1 and y1, and I'm going to have to refer to those. And I'm going to write this as y2 star is equal to y1 plus f of x1, y1, and I left off the h. Okay, so for us, that is y1 is 4.302 plus 1.5, and then whatever we get for f of x1, so we have x1, y1, we have to plug these two into the function. So I'm going to get the 3e to the negative x, which is 1.5, plus 0.4 times our y, which is 4.302. And let's see what we get. That is, okay, negative 1.059. So now we're going to plug this, we're going to use this in our new formula for y2. y2 is y1. I'll go ahead and write it down, plus h. F of x1, y1, plus f of x2, y2 star that we computed above, over 2. So this is going to give us 4.302 plus maybe I'll put the h is 1.5, and I'm going to put the over 2, h over 2, that's that. So now I can put in parentheses this plus this. F of x1, y1, we get negative, let's see, y2 is negative 1.059. Okay, it's negative 0.9406 plus, actually it's minus, plus a negative 1.0519. And if you plug that into the calculator, you get 2.808. So that means that x2, y2 is 3, 2.808. So it's kind of weird to think that y2 is actually our estimate at time 3, is y of 3, which is 2.808. That's what we were asked to find. So it was 2 steps, but it took us from 0 to the first step, 1.5, to the second step, out to 3. That's why it's out 2 time steps, but we took 1.5 unit time steps, so it took us to 3. And in this case, if you wanted your true error, how close that is to the true value, which was 2.763, you take 2.763 minus 2.808 over 2.763, and that relative error is 1.63%. Significantly better than using the regular Euler's method. This is substantially better, the improved method is, and I believe most of your homework will be doing the improved Euler's method.